Hello, welcome to the new episode of Organic Chemistry. This is ChemExplain. As you can remember, in the previous video, we talked about some forces between the molecules, and after that, we studied the physical properties of alkanes. But in this video, we aim to study some forces within the molecules. These forces can cause some different geometric arrangements in our molecules, so knowing these arrangements and knowing which arrangement is more stable and more favorable can help us understand the differences in chemical reactivity of different substances and molecules. Before starting, don't forget to like this video and subscribe to our channel for more chemistry content. Let's waste no more time and start this. Okay, I want to start talking about a really simple molecule, which is called ethane. A really simple alkane with 2 carbons and 6 hydrogens. So when we want to show molecules, basically we can use different models. But 2 of the famous models that we have here are really helpful. Let's go. Look at the one on the left side. When we want to show a molecule which is on the plane of the paper, we use the bonds which are like this, like these 2 hydrogens. On the other hand, when we want to show a bond which is out of the page, out of the plane of the paper, we use this sign. We can say that these bonds, these hydrogens, are coming to our face from the page, from the plane of the paper. On the other hand, we use these other signs to show that a bond or an atom is in the paper or in the plane of the paper. So this model is called hash-wedged. But on the other hand, we have another model which uses different colors of spheres to show different atoms and then connecting them together. We want to look at these 2 models in different situations to understand what is happening. Now, if you look at ethane from this direction, this is your eye, you look this direction. Let's call this carbon number 1 and this one number 2. If you look at this direction, you can see that the hydrogen which is connected to the carbon number 1 is exactly between the 2 hydrogens that are connected to carbon number 2. This can be seen with any other hydrogen and pairs that you want. For example, this one. If you look at this one, you can say that this hydrogen gets exactly between these 2 hydrogens when you look from this direction. I think it's easier to understand when you look at this model on the right. So again, this would be your eyes. You look in this direction, you can see that this hydrogen connected to carbon number 1 is exactly between the 2 hydrogens that are connected to the carbon number 2. Okay, but let's move to another geometric arrangement of ethane molecule. Let's look at this one. Now, again, we try to look from this direction. Carbon number 1 and number 2. If you look at this direction, you can see that this hydrogen connected to carbon number 1 and this one connected to carbon number 2 are exactly opposite of each other. Again, look at this one. This is your eye. You look from this direction. The hydrogens are opposite of each other. Not just one of them, but all of them. The pink ones together, the blue ones together, the green ones together, and more. So now we know that for ethane molecule, we have two different arrangements. Actually, to make it easier to refer to these shapes, we want to give them some names. For the first one, which the hydrogen from one carbon gets between of the two hydrogens of the other carbon, we call this staggered conformation. On the other hand, when the hydrogens are exactly opposite of each other, we can say that this one is eclipsed conformation. So, staggered and eclipsed conformations are interchangeably existed in a mixture of, let's say, ethane. And these two molecules, or better to say, these two conformations, can convert to each other really easily. So, to show it a little easier, we want to have a new model, which is called Newman model. In Newman model, we can understand the staggered and eclipsed conformation easier. Now, let's find out what the Newman model is. Okay, as you can remember the direction that we used to look from, we can see that here we are looking at the molecule from that direction. This one shows the carbon, which is in front, and this one shows the carbon, which is in back. So because it's a little hard to draw, and when it's drawn, it's a little hard to understand, we want to use the Newman model or the Newman projection. In Newman projection, we show the carbon, which is in the front, using a dot, and we show the carbon, which is in the back, using a circle. I'm sorry, I'm about to draw a circle. So this one shows the carbon in the back, and this one shows the carbon in front. Now let's look at this molecule. This one, the carbon here, is the front carbon, and this circle is the back carbon. You can see the connections with the hydrogens as well. The connections of the hydrogen and the front carbon are pictured completely, but the other connections, I mean the back carbon and the hydrogens, are pictured in half. So this way we can understand the conformation and the arrangement of the molecule a little easier. Now, knowing this concept and knowing the Newman model, we want to take a look at the conformations again to understand what is happening. Now, let's look here. We can say, starting from these molecules, one hydrogen gets between two other hydrogens of the carbon in the back. Okay, we want to rotate this molecule about the carbon-carbon bond for 60 degrees. If we rotate it, we can see that hydrogens are exactly opposite each other. Now we can call the molecule the eclipsed conformation. Again, if we rotate the molecule about the carbon-carbon bond, we can see that the conformation which we will have is the staggered conformation. But there is one important point here. If you look at these pictures, I mean the eclipsed conformation, you can see some signs here, some red signs between the hydrogens. Can you guess what these signs are showing? I think it's easy to say. They are showing some repulsion of same charges on some atoms. For example, hydrogens have a little repulsion between each other. When they are in the eclipsed conformation, their repulsion makes them a little uncomfortable. So they want to change into the staggered conformation. So naturally, when we have a substance and our substance is ethane, if we take a picture of the substance, at one moment we can see both conformations in the substance, in the sample. I mean, both staggered and eclipsed conformations exist. But because the eclipsed conformation is not really comfortable, is not really favorable or stable, it really tends to convert to staggered conformation as soon as possible. To understand this better, we want to draw a diagram showing the energy differences, or better to say, the potential energy differences between the staggered and eclipsed conformations of the ethane. Now, let's take a look at the diagram. Okay, so this diagram has two axes. This one shows the torsional angle, which I'm going to discuss, and this one shows the energy. As we go higher, the energy gets more. Okay, so as you look at the lower part of the diagram, you can see the staggered conformations. However, on the upper parts of the diagram, we can see the eclipsed conformations. And here, this green line shows the difference between the energies. As you can see here, at this level, all of the conformations are staggered. When they are staggered, it means there is almost no repulsion between the hydrogens of two different carbons. But at this level, we can see the eclipsed conformations, which have some repulsion between the two hydrogens of two different carbons. So because we have the repulsion, because the molecule doesn't feel comfortable and it's not favorable or it's not stable, the potential energy of the eclipsed conformation is always higher than the potential energy of the staggered conformation. The amount can be seen here, which is 2.9 kilocalories per mole. It means each mole of the, let's say, eclipsed conformation of this molecule has 2.9 kilocalories of more energy compared to the staggered conformation. And you can see here it is written torsional angle. What is torsional angle? Actually, the situation that two hydrogens are opposite each other and they have a great repulsion is called torsional strain. Or you can also say rotational strain. I'm going to write it for you. Torsional strain. It is the quality of the molecule which shows the uncomfortability, which shows the instability. So as we rotate this molecule about the carbon-carbon bond from the first situation, we are changing the rotational or torsional angle by 60 degrees each time. So you can see 0, 60, 120, 180, and goes on. So this diagram can help you understand the energy difference and the stability of these two conformations easier. So in general, we can say if we do not have any other special atom which is connected to the carbon or any other substituents, in a general term, we can say that this staggered conformation is more stable compared to the eclipsed conformation. Thank you so much. I think this is enough for today's video. In the next episode, we are going to find out that if some other substituents, some other groups, some other functionalities, or even atoms are connected to the carbons instead of the hydrogen, what will happen? How will the energy be? Or which one would be more stable? So thank you so much. Hope you found this video useful. If you liked the video, don't forget to hit that thumbs up button and subscribe to our channel for more chemistry content. See you next time.